All right, today we're going to tackle a data structure that's both surprisingly simple and incredibly powerful. It's called the Disjoint Set Union, or as you'll often hear it, Union Find. Now, if you've ever had to figure out how to manage connections in a network without accidentally creating messy, redundant loops, then you are in exactly the right place. This thing is a classic for a reason, and trust me, it pops up in technical interviews all the time.
So let's just start with a really common problem to frame this. Picture this. You're building a network. Could be computers, could be cities on a map, doesn't matter. You're adding connections, one by one. How can you be sure that the new connection you're about to add is actually useful and not just creating a pointless loop between two things that are already connected somewhere else down the line?
In the world of graph theory, that redundant loop has a name. It's called a cycle. And being able to spot these cycles, and spot them fast, is a really big deal. It's the key to solving a whole bunch of important problems, like finding the most efficient network routes or building something called a minimum spanning tree.
So here's the core idea, right? If you can already get from node A to node B through some path, they're already part of the same connected group. So if you then add a direct edge between them, you haven't really created a new connection. You've just created a cycle. The real trick, the challenge, is figuring out if that path already exists before you add the new edge and doing it quickly.
The solution to this is actually super elegant. It all boils down to just two fundamental operations. We just need a way to check which group a node belongs to and a way to merge two separate groups into one. That's really it.
So the first operation is called find. And honestly, the best way to think about this is to imagine each group of connected nodes as a team. The find operation is basically just asking, hey, who's the captain of this player's team? Every team has one single unique captain, and we'll call that the representative. So if you call find on the node, it'll just point you to the representative of its group.
And the second operation? That's union. This is what we do when we want to add a legit connection between two totally separate groups. Sticking with our little team analogy, union is like two different teams merging into one big super team. The operation takes two nodes, finds their captains, and then basically has one captain start reporting to the other. Just like that, two teams have become one.
And here is how it all clicks together. For every single new connection we're thinking about adding, let's say between node U and node V, we just run a quick check. We use find to see who U's representative is. We use find to see who V's representative is. And if they have the exact same representative, well, we know they're already on the same team. Adding this edge would create a cycle. But if they have different representatives, awesome. It's a valid new connection. And we use the union operation to merge their two groups.
Okay, so that all makes sense in theory, but how do we actually write the code for this? You might be picturing some complex, gnarly data structure, but the standard way to do this is so simple and clever. It all comes down to a single array. Here's the big idea. We model each group, each team, as a kind of tree. In this tree, every node just points to a parent node. And if you keep following those parent pointers up the chain, you'll eventually hit a node that's its own parent. That special node is the root of the tree, and you guessed it, that's the representative for the whole group. So how does this actually work with an array? It's really straightforward. We have an array, let's call it parent. The index of the array is the node itself, and the value at that index is its parent. So, for example, take a look at index 1 in the table. The value is 0. That just means node 1's parent is node 0. Now look at index 3. Its parent is node 2. Simple enough. But how do we know which nodes are the roots, the captains of the teams? And here's where it gets really clever. We mark a root node with a negative number. That's our signal that it has no parent. It is the representative. But we can make that negative number do double duty. We can use its absolute value to store the size of the group. So a value of -2, like you see for nodes 0 and 2, tells us two things. First, they're roots. And second, their groups each have two members. It's an incredibly efficient way to pack information.
But hold on, there is a potential trap here. What happens if our union operations end up creating a tree that's just a long, skinny chain? I mean, to find the root of a node at the very bottom, we'd have to climb up every single node along the way. That would make our find operation super slow and inefficient.
Thankfully, there are two amazing optimizations that totally solve this problem and make the union find structure lightning fast. They're called union by weight and path compression. I like to think of them as performance power-ups.
The first power-up is union by weight. This is just a really smart rule we add to our union operation. When we merge two trees, instead of just randomly connecting them, we always attach the root of the smaller tree to the root of the larger tree. Remember how we stored the size in that negative number? This is exactly why. This one simple rule helps keep our trees short and bushy, instead of letting them get tall and skinny.
So the key takeaway here is pretty simple. By just following this one little rule, we actively prevent that worst-case scenario of a long, stringy tree. We're always making the choice that helps keep the path to the root as short as possible for everyone.
Now, for the second optimization, path compression. And this one is just plain cool. When we run a find operation, we have to travel up the tree to find the root, right? Well, path compression adds one extra step. After you find the root, you go back along that same path you just took, and you make every single one of those nodes point directly to the root. What this means is that the data structure literally improves itself every time you use it. The very first time you search for a node might take a few hops, but you flatten the path on your way out. So the next time you search for that node, or any other node that was on that path, bam, the answer is just one step away. It's an amazing self-optimizing system. And you can really see the combined effect here. A naive implementation without these tricks can get pretty slow. Adding union by weight helps a lot, but when you put both optimizations together, wow, the performance is just incredible. The average time it takes to do an operation becomes so close to constant time that for all practical purposes, it basically is. So, why do we care so much about this? Because this isn't just some clever academic puzzle. This elegant little data structure is a critical piece of some of the most important algorithms in all of computer science.
For starters, it's the absolute heart of Kruskal's algorithm for finding a minimum spanning tree. That's basically finding the cheapest way to connect all the cities in a network. We've obviously seen how good it is for detecting cycles. It's also perfect for quickly finding all the separate, disconnected groups in any network. And it even pops up in things like image processing, where you can use it to group pixels of the same color together to identify objects.
Look, if there's one thing to take away from all this, it's that the union find data structure gives us an amazing way to answer these really fundamental questions about how things are connected. It takes a problem that feels like it should be complicated and just solves it with an approach that's both simple to code and ridiculously fast. And that kind of leaves us with a fun question to think about. This whole data structure is built on a really simple, intuitive idea, putting things into groups and checking their connections. So where else in the world of computer science, or maybe even outside of it, could this powerful way of thinking be used to solve other complex problems?